Okay, in this video I'm going to be going over types of reactions. We'll go through the types and then we'll go over how to predict products. It's going to include working with the activity series for single replacement reactions and the solubility table for double replacement reactions. So you're going to need your activity series worksheet, which looks like that. The back side should have your solubility table. And big assumption here is I am going to assume that you know your naming and you know your polyatomic ions. If not, just go back and learn those now, because this is no good if you can't name these compounds. Also, assuming that you know how to balance. So with those skills, let's see what we can do here. Anyway, the first type of reaction we can talk about is synthesis. And the basic idea behind the synthesis is you take two simple reactants, combine into one more complex product. Now there are extremely complicated synthesis reactions, but for Chem 1-2, we're just going to focus on simple synthesis reactions. For example, if you take magnesium and you burn it in air, what's that going to produce? Well, we just have magnesium and we have oxygen. There's only one thing these can possibly produce when you synthesize them. It's going to be magnesium oxide. So you have to work out the charges. Well, magnesium is 2 plus, oxygen is 2 minus, crisscross, and you simplify, so that's just MgO. And then you go back and balance it like that. Simple synthesis reaction. There's decomposition, which is just the opposite. When you have one complex product breaking down into two simpler one complex reactant, breaking down into two or more simpler products. Again, there are very complex decomposition reactions, but for Chem 1-2, we're going to focus on relatively simple ones. Just as an example, if I tell you iron 3 oxide decomposes into iron and oxygen gas, you should be able to write the formula for this. So again, here's where I talk about you need to know your naming. If you can't write the formula from that name, you can't even solve this problem. So iron 3 oxide, that's going to be Fe with a 3 plus. Oxide means O2 minus, crisscross, we get Fe2O3. Decomposes into iron. Remember, when we write metals in these, metals are just alone by themselves, just like this. Plus oxygen gas, so oxygen is O2. Don't forget your diatomics, which are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. See if I mixed any of these. Brinkel-Hoff. That's how we say it in my class, whatever you need to remember these. When these exist as in their elemental phase, or just when it's them by themselves, you pair them up like this. Another common decomposition reaction is the decomposition of hydrogen peroxide that breaks down into water plus O2 gas. And for again to balance here, let me go back up here. So even I'm going to need a 2 there, 3 and 2. Is that correct? Nope. 4. 2, 4, and 3. That looks correct. And then down here, let's see, 2 of these and 2 of these. Okay. By the way, this reaction, there's kind of two real-life effects you can see from this. When you buy hydrogen peroxide in the store, first of all, it comes in a brown bottle. That's because this reaction happens constantly, but it's sped up by UV light. So if it's sold in a clear bottle, basically your hydrogen peroxide would turn into water a lot faster. Even so, there's a shelf life on the bottle. It's usually 1 year. After 1 year, so much of it has turned into water that it's not very effective. And also, you'll notice there's a little hole in the top on some of it. Well, certainly on the stronger version, like the one that we use in a certain demo we do with, we call it Elvin's toothpaste, it's 30%, whereas the one you might buy in the pharmacy is 3%. The 30% has a hole in the top because so much oxygen is being produced, it needs somewhere to go. Anyway, that's decomposition. Next is combustion. Basic formula for this is a hydrocarbon plus O2 gas yields CO2 plus H2O. Now a hydrocarbon is an organic molecule. It's a mixture of mostly two elements, hydrogen and carbon. A lot of times with other elements mixed in like oxygen, nitrogen, and so on. Hydrocarbons are everything from wood to oil, coal, natural gas. Humans are basically made of hydrocarbons. Anything alive is some form of a hydrocarbon. And basically, when you burn them in the presence of oxygen, this does take a little bit of energy, but the energy you get out is a lot more. And this is why I'm able to, live in this society, is when electricity is generating right now. It's because this gives off a lot more heat and energy than needs to go into it. Technically, the energy is tied up in these hydrocarbons. Anyway, the basic formula is this. There's also something called incomplete combustion. Incomplete combustion is a hydrocarbon plus O2 gas yields CO, carbon monoxide, not dioxide, plus H2O. Incomplete combustion occurs when you attempt a combustion reaction in a place where there's not enough oxygen present. For example, if you buy a propane stove, it will say never use indoors or in a garage or a closed garage. Reason for that is if it runs out of enough oxygen to go through the reaction, it's going to produce carbon monoxide instead of carbon dioxide. Now, neither of these are good. This certainly leads to climate change, but this is more likely to be the silent killer that's going to kill you. So never burn any hydrocarbons in a closed room. Moving on, there is single replacement reaction. Replacement reaction. For short, I call this SRR, single replacement reaction. And this is when you need that activity series. Basic idea behind this is we have one element by itself, so we'll call it A, is going to react with BC, which is a compound of two or more things, two or more elements, I should say. And A by itself is going to attempt to bump one of these two out. Now, it could bump B out or it could bump C out depending on what element these happen to be. Generally, if A is either a metal or some kind of other cation, A is going to try to bump this other cation out. If A is something like a halogen, well, it's going to try to bump C out, which generally would be another halogen. So if it bumps A out, if A bumps B out, you're going to get AC plus B. Or if it bumps C out, you're going to get BA plus C. Right. It's easier with examples instead of these arbitrary letters. So let me run through a couple examples. All right, let's say we have lithium. Different color here. Lithium plus iron 2 chloride. Okay, so what happens here is lithium's by itself, so this is going to try to be like the bully. It's going to try to bump one of these out, and you have to think, is it going to bump the iron or the chlorine out? Well, lithium's a metal. It's going to bump the other metal out, and the real reason you know this is because lithium always forms a positive cation, Li+, so it only makes sense for it to replace the other positive one, because iron is positive and chlorine's negative. So if lithium were to bump the chlorine, you'd get iron lithiide, and that can't exist because you'd have two pluses together. So the rule is the cation is going to bump the cation, or an anion will bump an anion. But another thing you have to consider before you rewrite this equation is, will this actually occur? There's certainly a pecking order for things replacing, elements replacing other elements, and that's where this activity series comes into play. The way this works is the higher up, the more reactive or the stronger an element is able to bump others out. So you compare the two things, in this case lithium and iron, and you say, can lithium bump iron? So if lithium is higher up, then yes it will. If lithium is lower, then no reaction. And you can see right away lithium's the king. It's right at the top of the list. It's the most active element, at least in terms of metals. Here's iron way down here. So lithium certainly can bump iron, so yes, this will in fact go through. And now we write our formula. So lithium's going to bond with chlorine, but don't just simply write LiCl2 quickly. You have to pause and think about the ions involved. So that's going to be lithium chloride. And the way you figure that out is by saying Li plus Cl minus, crisscross rule, plus iron. The iron that gets bumped out is just regular old Fe. Even if there were like a 3 here, or a 2 or something, just regular Fe. You're now going to go back and balance it. So 2 chlorines, so let me do 2 chlorines, 2 lithiums, 2 lithiums, just like that. Let me just do one more, or a couple more examples of single replacement, just so we can see different types. Lead 3 hydroxide plus silver, Ag. Okay, so in this case, silver's by itself, so this is going to be like the bully. Silver's going to try to bump one of these two. Question is, which one? Well, silver always forms a positive charge, so it's going to bump the other positive charge out. So can silver bump lead? You look at your activity series. Silver, very near the bottom. Lead, a little bit above it. So therefore, no reaction. So you could just write no Rx for no reaction. Okay. Now, it's not just metals that are going to bump other metals. Occasionally, hydrogen can act as a cation in this case. So usually it's a metal trying to bump hydrogen out. But also, halogens can undergo single replacement reactions as well. Halogens being group 17 or 7A. For example, sodium fluoride plus iodine. Well, in this case, iodine is by itself. Now you might say, well, it's not by itself, there's 2 of them. Well, being what I call a Brinkelhoff or a diatomic, it always exists as 2. But this is just iodine as regular old iodine, not bonded to any other different element. So iodine is going to try to bump out one of these 2, and you have to, again, consider the charge. Well, iodine forms a negative charge. It's a nonmetal. So it's going to try to bump out the other negative charge. It's not going to try to bump the sodium out, because then you'd get iodine fluoride, which theoretically could exist as covalent, but in this case, it's not gonna do that. You're going to get a positive to a negative. So anyway, the iodine is going to try to bump the fluorine out. Can it do so? Well, you look down at the bottom. Fluorine is the king. Nothing can bump fluorine out. Here's iodine way at the bottom, so therefore clearly no reaction. And one more. Let's say we have chlorine gas reacting with... I don't need parentheses here, that's not polyatomic. AuBr5, which would be gold 5 bromide. Well, again, consider what's going to be like the aggressor or the bully. Well, chlorine's by itself. It's going to try to bump out bromine. Can it do so? Yes, it certainly can. Chlorine is higher. So therefore, we're going to get gold 5 chloride. Now, the charge on this gold has to stay the same. That's originally a gold 5 plus. I know that because it's bonded to 5 bromine 1 minuses. So this is going to be AuCl5, because chlorine is -1. Now bromine gets bumped, so you just write plus Br, but since it's a diatomic or a Brinkelhoff, we put a 2 there. You don't say Br5 just because there's 5 of them here. Bromine gets bumped and it exists as Br2. Now is when we go back and balance. 2 chlorines and 5 chlorines, the only thing that I could do is go like 2 here and a 5 there. Now I have 2 golds, 10 bromines, 10 bromines, 5, 2, 2, 5. Okay. Last type of reaction is double replacement reactions. Or let me write it out, double replacement. DRR, double replacement reaction. And the basic formula of this is always going to be the same. AB plus CD. 4 terms. Something like sodium chloride plus silver nitrate. 4 things. Now, this is going to react, and they're basically going to switch their cations or switch their anions. So A is now going to bond with D, because remember, positive, negative, positive, negative. This A has only one thing to bond to. It's not going to rebond to its own anion, because then there's no reaction. So if this does react, A is going to go with D, and B is going to go with C. But remember, when we write these formulas out, the positive one always comes first. So therefore, CB is my next product. AB plus CD, AD plus CB. Double replacement. Now with this one, you can't just assume all of them go through, because not all of them do. And for this, you need to look at your solubility chart. Now the basic rule for this is that you need 2 aqueous reactants, at least in the type of equations we're going to be doing in Chem 1-2. Now, there are cases where you can take gaseous or solid and react them, but for the vast majority of the problems we do, we'll tell you right off the bat that both reactants are aqueous. Reactants, of course, are the ones to the left of the arrow. And then for the products, and this is sort of more important, you need 1 aqueous product and 1 non-aqueous product. And by non-aqueous, I mean solid, liquid, or gas. But the vast, vast majority of the time, it's going to be solid. When you mix 2 aqueous liquids and you get an aqueous product plus a solid, that's called a precipitate. That's the noun form. That's the solid that forms is called a precipitate, and this reaction is called a precipitation reaction. Okay. Now this isn't a new reaction that you're going to categorize. Technically it's just a variation of double replacement reactions. Just like there's something called an acid-base neutralization reaction, that's just another version of double replacement. Anyway, let's get to a couple examples. Because part of this is we're going to be sketching these as well. That's very important to show that you truly understand what's happening with these compounds. So, imagine I have ammonium hydroxide, aqueous, reacting with aluminum sulfide, aqueous. Now, if I just told you those as text, as names, you would have to know how to write those. Again, naming is important here. All right, so let's write what the products are going to be. So first of all, aluminum is going to bond with hydroxide, so that's going to form AlOH3, and ammonium is going to bond with sulfide, so we're going to get NH4-2S. And now we need to check our products to see if this reaction will actually go through or not. Well, aqueous, we're good. Let's check on these. Aluminum hydroxide. Aluminum hydroxide, solid, very good. Ammonium sulfide. Ammonium sulfide, aqueous. The more you do this, the more you'll see there are kind of shortcuts. For example, ammonium, always aqueous. Acetate, always aqueous. Bromide, almost always aqueous. There's some shortcuts you can take. But anyway, our basic formula, aqueous, solid, aqueous. Therefore, yes, this reaction does occur. This is a precipitation reaction. And now we go back and balance. So let's see, 3 hydroxides. But now 3 ammoniums and 2 ammoniums, this isn't going to work. So when in doubt, double everything. Let me make that a 6 instead. So 6 hydroxides, let me put a 2 here, 6 hydroxides, 6 ammoniums, 3 sulfurs, and we're good. Okay, so that's the balanced equation. And now let's actually draw the sketch to go along with this, very important. Now when you draw the sketch, we generally draw 3 beakers. 1 beaker each for the reactants, and 1 final beaker at the end. And that's generally what happens. So you're mixing 2 beakers into 1, or technically 1 into the other. But we start with 2 beakers. And it's going to end as 1 beaker. Now your teacher may do something slightly different. This is just the rules that I'm following from my class, so make sure you follow whatever little stipulations your teacher does. We're all generally doing the same thing, but we might be tweaking it slightly differently. Anyway, since this is aqueous, it means my ions are now dissolved in water. So I'm going to show my NH4 plus ion and my OH minus ion above the bottom. My solids I'm generally going to write down here. My ions that are suspended in water or aqueous are going to be floating up here. Now what I'm going to add to this are water molecules. So your basic water molecule is HOH like this, and there are partial charges on it. Hydrogen is positive, hydrogen's positive, and the oxygen is negative. Now that doesn't necessarily mean the ions aren't canceling each other out. These are just technically partial charges. The 2 H's and the O balance each other out nicely, but oxygen has sort of a slightly negative edge to it. Hydrogens have a slightly positive edge. So what we're going to do is simplify that down to just a little ball and stick model like this. And that's going to represent a water molecule. Negative oxygens, positive hydrogens. So let's draw them. You need to make sure you arrange them in the proper direction. So here I have a positively charged ammonium ion. Which end of the water is going to face it? Well, it only makes sense that the negative side, or the oxygen side, is going to point towards the positive ammonium. Let's draw a couple more, just like that. Here I have hydroxide. Which side of the water is going to face hydroxide? Well, it's going to be the positive end, which are the hydrogens. So let me draw a couple more hydrogens, like that. That's how you need to draw this. And what that shows is, when I have ammonium hydroxide, I don't have like a solid ammonium hydroxide, or I should say when it's aqueous. I have a mixture of water with ammonium and hydroxide ions floating around in it. Let's do the same thing here. Aluminum. Let me do this in black. Aluminum, 3 plus, sulfur, sulfur 2 minus. Let me add my water molecules. So the aluminum's going to positive, so it gets the oxygen end, which is the negative end. Like this. Sulfur is negative, so let's attach our hydrogens. Not attach, orient them towards it. Okay, so that's a good representation. Now you'll notice we have 2 of these and 3 of these. I am not going to make you draw 2 of these and 3 of these because you're going to fill your whole paper. We're going to waste all these, trees on this. So all I'm going to say is draw 1 of each. You'll see we're going to make a little adjustment to that at the end to make sure we're clear with the law of conservation of mass. And here's my final beaker. Now, your aqueous product needs to be suspended in water just like these aqueous reactants. So this is aqueous, so I'm going to have ammonium, NH4 plus, and I'm going to have S2 minus. Let's draw our water molecules. Again, the oxygen faces the positive one. The hydrogens face the negative one, like this. My solid product is not aqueous. It's not going to split up floating in water. And where do the solids end up in the beaker? They settle at the bottom. So here's my aluminum hydroxide. Notice you don't put any charges here because when it exists as a compound, it's stuck together and it's uncharged, basically. It's stuck together. There's my drawing. I have aqueous ammonium hydroxide with aqueous aluminum sulfide reacts to form aqueous ammonium sulfide and solid aluminum hydroxide. Now, because this isn't a true representation of the proper number of atoms involved, we're just going to note down at the bottom that the above sketch does not obey the law of conservation of mass. Just a little disclaimer for ourselves. Otherwise, it would take a lot more paper to draw these. Okay? So yes, it's a lot of work. Are you going to have to do like 10 of these on the test? Of course not. But you have to understand how to do this because this truly shows a deep understanding of what chemistry really is. It's not just the atoms bonding. It's about how they react with the water around them. We're going to do one more example. Let's say we have sodium nitrate, aqueous, reacting with barium oxide, aqueous. Okay, so let's write our products first. Barium is going to bond with nitrate, but don't just quickly write BaNO3. You have to pause, balance out the ions. So barium is 2+, nitrate is 1-, crisscross rule, Ba, parentheses, NO3, close parentheses, 2, plus sodium bonded with oxygen. Again, don't just write NaO. It's going to be Na2O. Now we predict, or we state the state symbols, or solubility. Barium nitrate. I know from a shortcut all nitrates are aqueous. Let's double check. Barium nitrate, aqueous. Sodium oxide. I also know from shortcuts that sodium is always aqueous as well. Sodium oxide is in fact aqueous. Aqueous, 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 aqueous. No reaction. No reaction. Now when there's no reaction, I'm not going to require you to balance it. Your teacher may. Follow your teacher's instructions. But I am still going to require the sketch. In fact, the sketch should show nice and clear why this is in fact no reaction. So I'm going to do this one a little bit quicker because hopefully you got the full explanation before. Na+, NO3-, Ba2+, O2-. Let me raise that up a little bit because I don't want people to think that's solid on the bottom. Let me add my waters. Ba. Okay, those are my aqueous reactants. Let's look at my products. Both of these are aqueous, so I'm going to have 4 things floating around in water. Barium, nitrate, sodium, and oxide. Let me add my waters. Positive, so the O faces that, O faces that. Doesn't matter how many you do. I think 2 or 3 is fine. Sodium, this is positive, so again, the oxygens face the sodium. Nitrate and oxide are both negative, so therefore the positive hydrogens are going to face this one. There we go. So if you really look at what happened here, we had 2 ions floating around randomly in water, 2 more ions floating around randomly in water, dump them together, 4 ions randomly floating around in water. Is there any reaction? No. You just made ion soup. You had 2 bowls of ion soup, now you have 1 bowl of ion soup. No reaction. Alright. These are 8 questions. I suggest you pause the video, try to work out these 8. Note the instructions, identify the type of reaction and the products of the following reactions. If they occur, balance them. Include state symbols where appropriate, meaning where I give you or where you can clearly, obviously figure out what the state is going to be. For double replacement reactions, include a sketch, whether they go through or not. Don't worry, there's not like all 8 of them are double replacement reactions. So pause the video now, and I'll get started on these right now. Alright. I just realized I forgot to write each one on its own slide, so I'm going to be going back and forth a little bit here. Number 1, table salt, sodium chloride is added to a beaker of liquid mercury. So, NaCl, since we said table salt, we can call that solid, plus mercury, liquid. Alright, well, first, what type of reaction are we looking at here? This is going to be single replacement. This is by itself. Mercury is going to try to bump sodium out because they're both metals, or more specifically, they're both cations. So can mercury bump sodium? You take a look at your chart. Sodium, mercury, no it cannot, no reaction. One down already. Number 2 says nitrogen trihydride gas decomposes into hydrogen and nitrogen gases. It's actually the opposite of a famous cycle called the Haber cycle, which allows for fertilizer to be made. Something they say saved or allowed the world to grow to billions of people without starving. Anyway, nitrogen trihydride. Nitrogen trihydride, also known as ammonia, not ammonium, ammonia, is going to decompose, so right there it tells you the reaction, decomposition, into hydrogen gas, but that's paired, plus nitrogen gas, again paired. And do I tell you this is a gas? Yes, gas, gas, gas. Let's add the state symbols. And let's balance this out. So 2 nitrogens and 6 hydrogens, done. Number 3, aqueous sodium hydroxide is added to aqueous potassium phosphate. All right, sodium hydroxide is going to be NaOH, aqueous. Aqueous potassium phosphate. Potassium phosphate, now phosphate's 3-, so it's going to be K3PO4 aqueous. Type of reaction, double replacement. We look at 4 terms here. Sodium hydroxide, potassium phosphate. They're going to rearrange themselves. Products being sodium phosphate, Na3PO4, and potassium hydroxide, KOH. Now we need to identify the states. So potassium, one of my shortcuts is it generally almost always forms aqueous. Let's double check. Yes. Sodium phosphate. Aqueous. Therefore, no reaction. We had aqueous, aqueous, yields aqueous, aqueous. Again, we just made ion soup. No reaction. But we still have to draw the sketch for this. All right. NaOH aqueous. Na plus, OH minus. Let's see. O's are going to be facing the Na. K plus, PO4 3-. O's facing the K plus and away from the phosphate. Yields aqueous and aqueous. So we have NAs, we have PO4 3-, we have K pluses, and we have OH minuses. Let's add our waters. OH minus, so that's going to be the positive hydrogens facing it. 3-, so my positive hydrogens are going to face that. And my K plus gets my negative, like that. Okay? By the way, I realized I forgot to write my disclaimer statement on the last problem I did, but I would end this by saying the sketch above does not obey the law of conservation of mass. Just saves you the time of writing all these out. All right, we're done. Number 4, tricarbon octahydride, aka propane, combusts. Tricarbon octahydride is that, C3H8, combusts, means plus O2 gas, yields CO2 plus H2O. This is a combustion reaction. We need to balance it out. So C3, so let me try a 3 here. Well, let me start with my hydrogens. It tends to work out well for me. 4 hydrogens, or 8 I should say, matches the 8 here. Let me balance my carbons. 3 carbons, 3 carbons. And now all I really need to look for is, do I have an odd number of oxygens on this side? Even, sorry. Do I have an even number? And if I do, any number can go here and we're good. So I could see I have 4 and I have 6, so therefore 10. I'm good. Go to 5. We're done. Okay. Number 5, an iron nail dropped into nitric acid, HNO3. Iron nail, solid, drops into HNO3. Now, when we do acids and bases, later in the year, you'll learn all acids are aqueous. In fact, HNO3 by itself is hydrogen nitrate, but when it's aqueous, it's now nitric acid. Anyway, are we going to see a reaction here? Well, this is going to be single replacement. Iron's by itself, so think of this as the bully, and iron's going to try to bump out one of these two. Now, in this case, the old metal bumps metals doesn't quite work because I don't see any metals here. So that's why you have to think cation, because iron is always positive when it's ionic, is going to bump the other cation, plus. So iron's going to try to bump hydrogen. Can it do so? Hydrogen, iron, yes it can. So we're going to get, I forgot to put a state charge here. Sorry, you can't complete that one without it. I should say something like iron 3 or iron 2. Anyway, iron, so assuming it's 3, iron 3 nitrate is going to be FeNO3, 3. And hydrogen gets bumped out, but because it's a Brinkelhoff, it's H2, and that's generally going to be a gas. That's why you would probably see some steam going off, or not really steam, but bubbling. You would see bubbles of hydrogen gas. And let's make sure we're balanced here. So let's see. I can kind of tell already what I need to do, but let me go through it. 3 nitrates, but the problem is with H2, this needs to be even because I can't balance H right now. So when in doubt, double it. 6, 3, 2, 2. 2 iron, 2 iron, 6 hydrogens, 6 nitrates. We're good. There it is. All right. Good. Aluminum burns in air. We'll call that solid. Burns in air means plus O2 gas. Well, this is not going to be combustion. Don't mix that up. Don't say CO2 and H2O because that makes no sense here. Just because something burns doesn't mean it combusts. So the only thing these can possibly do, I mean, there's no replacement here. It's not like anything can happen. So there's got to be synthesis. So aluminum's going to bond with oxygen to form aluminum oxide. So you just got to look up the charges on these, and you'll see aluminum oxide is Al2O3. Technically, it's going to be solid, but it wouldn't be required to write that unless you knew the compound. Let's go back and balance. I'm going to need a 2 here and a 4 here. And a 3 here. Number 7, manganese 2 sulfate is mixed with sodium carbonate. Manganese 2 sulfate is mixed with sodium carbonate, Na2CO3. I should have told you both of those are aqueous, because otherwise we're wrong already. And these are going to form, well, first of all, we're looking at a double replacement reaction. So manganese is going to bond with carbonate. And something to note, this being a transition metal, it can have multiple charges. But the manganese is going to keep the same charge it had before. So right now it's a manganese 2+, and you know that because sulfate is 2-. So we're going to keep the manganese 2+ bonded with the carbonate to form manganese 2 carbonate, which is this, plus sodium sulfate, which has to be Na2SO4. Now we look up the solubility. Okay, manganese 2 carbonate is solid. Sodium sulfate, sodium is always aqueous, and yes it is. So therefore this does in fact go through. Aqueous, aqueous, solid, aqueous. This is a precipitation reaction, a type of double replacement. So now we have to balance. So let's see, manganese is good, sulfate's good. Looks like we're good, all ones across the board. So let's do our sketch. All right, manganese sulfate, manganese 2 sulfate aqueous means Mn2+. and SO4 2 minus. Let me do this real quick. Na plus and CO3 2 minus. Let me add my waters. So positive, the O faces the positive. The hydrogens face the negative. Just like that. Over here, let's draw my aqueous product. So that's going to be Na floating in the water and SO4 2 minus floating in the water. Draw my waters. A little better. And my solid product is manganese 2 carbonate, which sits at the bottom like that. You could even put solid. Okay, there's my solid at the bottom. Nope, no charges on that. And we write the same thing down here. The above sketch does not obey the law of conservation of mass. All right, we have one more. Chlorine gas is added to silver fluoride. Let's check my spelling on fluoride. Chlorine gas, that's going to be Cl2 plus silver fluoride. Single replacement reaction. The one that's by itself is chlorine. So chlorine's going to try to bump the fluorine out because they're both anions. Can chlorine bump fluorine? No, it cannot. No reaction. Okay, here we go.